Hi, everyone. I'm Munib. I'm a co-founder of Blockstack Labs, and I'm also just finishing my PhD at Princeton University. And this is work with Jude, who's sitting right here, Ryan Shea, and Mike Friedman from Princeton. So basically, today I'm actually going to outline a very generic problem with security online, like how we use the internet, and give you like some background on blockchains if you guys like don't know anything about it, and then discuss like how we can actually use blockchains to make internet communication more secure, right? I'll give you some lessons we learned from a production system that we deployed for more than 2 years, and the design of a new system that was actually informed by the experiences of our production system, right? So first of all, there is a very high-level general problem with the internet that, let's say you're sitting there, it's your laptop, and you want to go and visit Facebook.com, right? Facebook has all your data. They have all your pictures. Like it's a separate problem that a company actually has access to all your messages, all your photos, and so on and so forth. And then they implement some sort of an authentication mechanism, right? It's usually a database. They give you a password and a username. And from your laptop, when you're accessing the internet, you would talk to some DNS resolver, right? And you'll try to resolve Facebook.com to an IP address. And you will also talk to some PKI service, most probably VeriSign, right? So these are usually companies. ICANN is a nonprofit organization. And mostly you're talking to a company like VeriSign that says that, hey, trust me, this is Facebook.com, right? So if you kind of squint your eyes and look at the bigger picture, these are a bunch of remote databases that you're kind of blindly trusting. Right? DNS is a database of mappings between human-readable names and IP addresses. And then similarly, security certificates are a database that some company operates and says that, hey, trust me, this is the correct information for Facebook. And once you enter Facebook, again, they have a database of authentication information that, hey, this is your password, this is your username, and you can actually log in, right? So in an ideal world, we should be able to build a system that has a global database that no one owns, no single company owns that, right? Otherwise, that company becomes a monopoly online. Imagine that Facebook just says, I'll run DNS, I'll run PKI, I will keep all of your credentials, and whenever you want to use the internet, just log into Facebook first, and then you can use the internet, right? So that company would naturally become a monopoly online if you allow a system like this. So what you want is a completely decentralized DNS system paired with a completely decentralized PKI system and a decentralized authentication mechanism. And what we're proposing is that you can actually do this today using blockchains. That actually lends us into what exactly is a blockchain and how can they help, right? So just look at this picture. This is me, Brian Kernighan, and Paul Krugman, who hates Bitcoin and blockchain, by the way. And we are trying to design a new cryptocurrency. So imagine it's just a piece of paper. We are all sitting in a room at Princeton. And I have 8 coins. Brian Kernighan has 10. I gave 2 to Paul. And when I did that transaction, we were all in the same room, right? So there's no inconsistency. We can all see the state on the piece of paper. But let's say Bill Gates joins and he's in Seattle. And now I want to send a transaction to him. So basically the problem is, how do we make the state at Princeton consistent with the state that Bill Gates is seeing in Seattle? So that's the main problem, which basically boils down to having a distributed ledger, which is what a blockchain is. And how they implement it is basically just a file, right? You can download it. I started working in blockchain in 2013, it used to be less than 20 gigs at that time. Now it's around a 60 gig file particularly for Bitcoin. You can view it as an append-only global log, right? So there's a leader election process, and these are what are referred to as miners. So they're solving these hard problems, which are hard to find a solution to, but very easy to verify that you got the correct solution. So all of these miners are in a race to become the next leader, and the next leader gets to write the next block, right? And the ledger just keeps growing. And the interesting property of this ledger is that as your data gets old it gets more and more secure, right? So you might have heard about a 51% attack on Bitcoin. Let's say a single miner can have like more computing power than other people. Even that miner can only do certain limited things with the blockchain. Maybe they can do some things with the last 6 blocks or do a limited attack. But data that is like weeks old or months old, the amount of computation power required to go and tamper with that data is extremely, extremely large. So we actually use that property, and we say that we'll just use blockchains for total ordering of operations and build DNS and PKI on top of that. Right? So obviously there are some challenges with blockchains. You can't store a lot of data because everyone needs a copy. It's extremely hard to introduce new features to blockchain. And this, in retrospect, actually turns out that this is actually a good thing. Right? Once blockchains get popular, it's extremely hard to change them and get the miners to upgrade without breaking consensus. Right? And I'll discuss like how we use this property in our solution. The writes are slow, like every new block comes in like roughly 10 to 40 minutes. So you have to design your system accordingly. And they have the endless ledger problem. The blockchain just keeps getting bigger. So if you're a new node and you need to audit the blockchain from the beginning before you actually boot up, it will require some time. Right? So we'll keep these challenges in mind when we talk about Blockstack. So we set out to build a blockchain-based DNS and PKI system back in late 2013, and we launched the system in March 2014, and this is what it looks like. So this is Werner Vogels. He made an account, the CTO of Amazon, and the interesting thing about his profile is that he just looks like a very normal, like about.me kind of a profile or like a Twitter profile, right? So he registered Werner, which is actually registered as werner.id. So they're namespaces, just like DNS, like .com, .net, .org. This is like the .id namespace. And he owns this name and all the data associated with his name with the private key exactly as how you would own Bitcoins on the blockchain. So it has the exact same security property that if you want to change a single character in his profile, you will have to do an attack with which you can actually steal Bitcoins, right? Like either attack the blockchain or steal its private key, right? And attacking the blockchain is actually not easy at all. Like it will require a state-level actor or more than $1 billion to be able to actually launch an attack on the blockchain. So this is kind of like the security model. There are no third parties. Directly with a private key, you can actually own a name and your certificates. You can also post proofs saying that, hey, this is my master identity on the blockchain. So this is Sir Tim Berners-Lee who signed up, and he's posting on Twitter saying that, hey, this is my identity that I created on the blockchain. Right? And similarly, there are many other proof mechanisms, and I won't go too much into it because I want to focus on the system side in this talk. So this was our original system. You know, we were actually using a smaller blockchain, and we were literally putting all of this information in the blockchain itself. Like it doesn't scale. We don't do that anymore. But this was basically a smaller blockchain called Namecoin. So back then, it wasn't clear if for different applications you would have different blockchains, or would people start converging to a single blockchain. Right? So we started off on a smaller blockchain. We ended up migrating because of issues, and I'll discuss them. So these are kind of like the lessons from our production system. We were using a u/namespace. Think of this as like a TLD. So we started a new TLD on the Namecoin blockchain. We were live between March 2014 and August 2015 on Namecoin. We did around like 33,000 registrations on the network, which was around like 200,000 transactions. And 200,000 transactions on a blockchain is a lot, right? Like they're not designed to take that much load. So the first thing that we noticed was that your blockchain is really secure as long as no single party has more than 50% of the mining power, right? And on Namecoin, we actually started noticing that there was one miner that had more than 50% mining power, which is scary, right? But what was more scary is that no one noticed. We were the only player who actually noticed that this is going on, and everyone else was just using Namecoin without even noticing this. So the lesson for us was that you need to be on a bigger network, which is used by a lot of people, so that if something like this is happening, the community would actually notice that this is happening and they would be able to take some action, which is exactly what happens on Bitcoin, which is by far the largest blockchain. And the situation actually got worse. We noticed this for the first time in December of 2015. We started building Blockstack, and by the time we actually did the migration 8 months later, the single miner had up to 75% of the mining power at some point. At that point, it's a centralized system. Like that miner can pretty much do anything if the miner wants to. So I wouldn't go over all the lessons. I just want to point out one networking lesson because it would be interesting to this community. So usually you would have like between 10 to 40 minutes between blocks, but there was 2 weeks in which the average time went up to like 250 minutes or something like that. So basically what was happening was someone was sending transactions with a lot of outputs, which was crashing miner softwares, right? And miners kept crashing and kept coming back, and this was like a network reliability issue for us, right? So imagine that for 2 weeks, all of our registrations are just queued up, and we are unable to broadcast them on the network. And we have a lot of other lessons as well. I would just refer you to the paper because I really want to talk about the new system. So for Blockstack, like here's the vision that we have. So we are already working with, I don't know if you can read this, but the logo is called Bitseed. It's a company. They manufacture like these hardware devices that will give you a full copy of the Bitcoin blockchain, right? And we can run our Blockstack server on this as well. And this device, you can just plug it in a room. It boots up. It fetches the copy of the blockchain, verifies it, and runs Blockstack on top of it as well. And this is another company, 21. They also manufacture these Bitcoin hardware devices. And they can actually, once these devices boot up, they can become your security box, right? Your laptop can directly talk to them. And your laptop does not need to trust any other system on the internet. Like this security box is your DNS, this security box is your PKI system, this security box is how you verify that, let's say, Jude was sending me a message, I would verify his identity, and I would check his public key, and I will know that, hey, this is actually Jude who's trying to talk to me, right? So this is an implementation of David Clarke's trust-to-trust principle, that, which is a variation of the end-to-end design principle that communication on the network should only happen between two trusted endpoints. Right? So this is one endpoint, and that is the other endpoint. And that's the internet that we want to see, where you would be in a trusted zone, and you do not need to depend on any other trusted party outside that zone. So how do we build this? The first layer in Blockstack is the blockchain. And it's extremely important that we are agnostic of any particular blockchain, right? Because our experiences on Namecoin showed us that you might need to actually migrate from one blockchain to another. So how we have designed the system is that it just treats the blockchain for total ordering of the operations, and that's it. We can be on any blockchain. Our only requirement is we should be on the most secure, most used, most reliable blockchain. Today it happens to be Bitcoin. If 5 years from now it's something else, we'll just migrate over. Naming is what I already described. It's like DNS, right? So it's already built. We have a DNS system operating on top of blockchain. Identity is the profile of Werner Vogels that you saw. Right? So you can actually like get a username, build a profile, and like prove that, hey, this is actually you. And once you do that, authentication becomes trivial, right? Like if there's a website, you go and you basically I want to log in as munib.id. That website would check the blockchain and give me a challenge that proved to me that you own munib.id. And I would just sign a message as a response to the challenge, and I'm logged in. No more passwords. This is your universal login for all of the internet, right? And we already have open source libraries that do this. Applications are already integrating this, right? And from a business point of view, the idea is that no single company can actually own your universal username for the internet because that company becomes a monopoly. So this has to be decentralized. No single company can actually own this. So once you have all of these layers in place, the last layer is storage. Right? And the view that we take of storage is that we treat cloud storage providers as dumb hard drives, and we put encrypted data blobs on these dumb hard drives. Right? You can use any cloud provider. We write drivers for them, and you're basically pointing your blockchain entry to the storage provider. Right? And I'll tell you more about it. And then people can start writing apps on top of this stack. So this is basically how we operate on the Bitcoin network. The purple nodes are the Blockstack server. And one server just needs to talk to any single Bitcoin node. Right? So it could be local. You can package them as the same piece of software as well. Right? And the Bitcoin network is a peer-to-peer network, and they talk to each other, and they do consensus. And we just free ride on top of the consensus that the blockchain layer is giving us. So this is the first layer, the blockchain layer. Again, we only rely on total ordering of our operations. This layer does not understand the new operations that we are broadcasting in Bitcoin transactions. Right? Those operations only make sense to our virtual chain. Right? Let's say I want to introduce a new feature, name register, that is not present in Bitcoin. If I want to actually implement it at the blockchain layer, I would actually have to go and convince the Bitcoin community and the Bitcoin miners that, hey, this feature is important. You should actually have a name registration where you can register human readable names. And that process, in practice, just does not work out. Right? Bitcoin community argued for more than a year to change their block size from 1 MB to 2 MB, and it didn't happen. And there are good reasons for it. Right? It's a consensus-breaking change. And you can do that at that layer. But in our virtual chain layer, we can actually introduce new functionality. And the functionality that we introduce is that you can register a domain name. You can own it using a public key or a Bitcoin address. And you can have a hash of the zone file, which is exactly the same thing as a DNS zone file associated with it. Right? So our Blockstack server would process this information and build a database locally of this information. The next layer is routing. Which is basically zone files. I'll just show you an example of zone files. This is for Werner.id. There's a TTL, and it just points to the storage endpoint that he's using. Right? It's extremely simple, exactly the same thing as DNS, but the interesting thing is that the hash of this zone file is recorded and can be verified using the blockchain. Right? So you cannot tamper with this information. And the last layer is storage, where, as I said earlier, that we write drivers for all of these different storage providers. And you're basically following the pointer that is there in the zone file to go to the storage endpoint, fetch the data, and you can actually either hash the data and check the hash of the data, or you can just check the signature because you also know what is the public key that should be signing this message. Right? So it's a completely decentralized storage system. But it has the performance benefits of cloud computing. So I think I've already discussed this, that you need to be on the most secure blockchain and be able to migrate. Blockchains, you cannot put a lot of data in them. With this system, you can actually put unlimited data because we are just using cloud storage backends. It's extremely hard to introduce new features in blockchains. We introduce a virtual chain layer where you can just write a new state machine and introduce new features there. And blockchain writes are slow. In our system, you only need to do the initial registration on the blockchain, and then every operation afterwards, we take it off the blockchain path. So it's actually extremely fast. I'm actually running a bit short on time, so I'm going to skip this. This is basically a fast bootstrapping mechanism where we imagine like a consensus hash that incorporates all of the earlier operations which were done in the blockchain, right? So you can actually take this consensus hash and go back to this like secure internet model, and you can even call your friends and ask like, hey, this is the consensus hash that I'm seeing. What is your consensus hash? Or you can actually like talk to universities or Microsoft or Google and check with them that, hey, am I on the same consensus hash as you? So this is a way for you to check that, hey, am I on the secure internet or not? We also use this for fast bootstrapping. Basically, if you know a consensus hash that you trust, you can actually do a skip list and follow pointers and very quickly go back in the blockchain and try to verify, let's see, some operation that was done here. Right? So the details for this is in the paper. You can go and read that. So this is currently the largest non-financial production system running on top of Bitcoin. right? So people started using Bitcoin for non-financial things, and we are one of those systems. And this is basically other protocols that are also trying to do non-financial things with the blockchain, which in our view is going to be the majority use case, right? Like Bitcoin came around as a financial thing, but it actually has a lot of value in non-financial use cases. So over here, like this is in the paper, we basically just do a quick overhead comparison. The main takeaways are that our system is mostly network bound. It basically adds around 5% overhead in terms of the encrypted information to files, right? And that's it. The rest of it is like exactly as like talking to S3 or G Drive. In terms of the CPU overhead, it's like roughly 2 seconds for a 100 MB file, but most of the times you're just going to be network bound anyway, and you won't be CPU bound. We are working with multiple blockchains now in a way to like scale as well. Just like the .uk domain is managed by the United Kingdom, you can have a particular TLD that lives on Ethereum or lives on like some other blockchain. And people are coming to us trying to start new namespaces, like a .git namespace for software packages, a .iot namespace for Internet of Things devices. You can actually go and download the CLI, just do pip install Blockstack. You can start doing lookups. You can start registering names directly on the blockchain. And this is not my work, right? There's a lot of people involved. Some of them are in this room. There are professors involved from Princeton. We have around 900 community members and open source developers. And Microsoft recently actually started working with us, and they're pushing this internally at Microsoft and deploying it. So I'm happy to take questions. All of our code is open source. It's at github.com/Blockstack. We are aggressively hiring, and we are having a BOF session on blockchains later tonight. So please come there and say hi.
Hi, yeah, I'm Ben Reed from Facebook. How do you know when somebody registers a name that it belongs to them? Like, can I register chase.com?
Yes, so I would separate name registration from who you are. The name registrations are first come, first served, like domain names. So you can just go and register chase.com before chase.com and then try to sell it to them. And there's already a second market forming for people registering names and then selling it to other people. I think Cameron Winklevoss bought his name for a lot of Bitcoins. And so the other question is like who you are. So that's your identity. That's not the name, right? Like I'm Darth Vader as well on the blockchain. But it's basically the proofs you have around who you are, and you can also get statements from third parties. For example, Bank of America could actually sign a statement saying that you're over 21. Whatever the name that was that you registered, that this person is over 21. And at that point, you're trusting the party that signed that information, very similar to how VeriSign signs that, hey, trust me, this is Facebook.
Right, so if like spammers or whatever came into one of the domains you set up and registered a bunch of big name domains.
Yeah, absolutely.
Couldn't that effectively kill your...
Yeah, absolutely. This actually happened to Namecoin. So there's another professor at Princeton, Arvind, who did an analysis. So on Namecoin, people registered like around 190,000 names, and less than 1% were actually being used as domain names. So the issue there was that their pricing function was really flawed, and names basically became effectively free after a couple of years. What we do in Blockstack is that we let you define extremely complicated, sophisticated pricing mechanisms. For example, on the .id namespace, short names are extremely expensive. If you have numeric characters or underscore or something, the price of the name drops. And starting TLDs also costs a lot. When we registered the .id namespace, we actually burned $10,000, which in today's Bitcoin terms are actually $30,000. And this was on top of Reddit. People were trying to figure out that who is this stupid programmer who just burned $10,000. But that was actually, you're paying a price. So there's a price tag on these registrations. So if you're a large domain squatter, you will have to pay a price just like you would have to pay a price on DNS.
Right. Okay.
Hi, I'm Amar from Microsoft Research. Love your talk, especially the fact that it's also real and usable. Could you talk a little bit about migration? What's involved in migration? Is it computationally very expensive?
Yeah. So basically, how we did the initial migration was that we announced a block. So you can also think of blocks as time, right? You can go back in history, and you can also say that at this block, that is like a future date, the state on Namecoin is no longer going to be valid, right? And let's say we were migrating to Bitcoin. How you start namespaces is, what I didn't get into is all name registrations are two-phase commits. So first you announce a hash, nobody knows what the hash is, and then after you have enough confirmations on a name, you say that, hey, this was the actual name that I was trying to register. Same happens with TLDs as well. So we started the .id TLD, nobody knew what it was, and between the time like you do the registration and the namespace is actually ready, it's a separate operation, it's like a lock that you acquire. So you can actually register things in that namespace before you release the lock. So this is how we did the migration from Namecoin to Bitcoin. It's like we acquired the lock on Bitcoin, we migrated everyone over, and we released the lock, and it's all public information. People can see that the state on Namecoin until a particular block is exactly the same state that we transferred over to Bitcoin.
So if there were a lot of blocks already present to this new system that you were moving to, how much time does it take effectively?
How much time does it take? So it's basically that depends on the bandwidth of the blockchain you're moving to. Bitcoin gives you roughly 1,500 transactions per 10 minutes, right? But we are working on different ways of actually scaling that up as well.
Okay, thank you.
Hi, thanks for the presentation. Chuck from Korea University.
Mm-hmm.
I'm just curious that why you want to utilize Bitcoin network, because Bitcoin network is mainly financial oriented network, whereas yours totally different goal, and I'm not sure that they means that Bitcoin community allow you to write on their network.
Yeah, absolutely. So basically, so this was one of the lessons we learned from Namecoin, is that starting new blockchains is extremely hard. Think of blockchains as that you can attack them easily earlier in time. Let's say I started a blockchain today. It won't be very stable for a very long time until there are enough miners and enough infrastructure in place for that blockchain to be secure. Bitcoin today is extremely secure in terms of how much money you will need to spend to try and attack this blockchain, or how much infrastructure or ASIC cards you would have to manufacture to try and attack this blockchain. And as far as it's only meant for financial uses, I would say that it's basically an open network where you're effectively at the end of the day paying a price for secure storage. That you just want to store certain bytes, then they can mean anything to anyone securely in a blockchain, and you're paying a price for it.
So that means that anybody can just write on top of Bitcoin.
Yes, you can. People already are. This is I think $1.1 billion have been invested in this space over the last 3 years. So there are so many companies working at different layers. So it's an entire industry now.
Okay, thanks.
I'll round it up with one question, which is it practical to use this? Because you yourself said that the pace of updates is very slow. Imagine putting billions of people and having all their organizations register their domains with Blockstack.
Yes, absolutely. So this question came up with Microsoft, right? Microsoft, the first thing they were talking about was, hey, how do we register 1 billion people on the blockchain? So there are two answers. One is the slide I had about different TLDs on different blockchains. So imagine that the Bitcoin blockchain is the global blockchain. You follow a pointer and you say the .microsoft domain runs on this blockchain, and it has different properties. Let's say it's a federated blockchain run by Microsoft and 2 other big companies, and you can do registration at line speed there, right? So it's a trade-off between speed and decentralization. There are different knobs that you can play with.
But then it's run by Microsoft. You're back to Verisign.
Absolutely. So the second solution, we think of this as different namespaces that have different properties, right? So the second solution is similar to having subdomains, right? But you can actually have a cryptographic commit of the subdomains where the original owner cannot revoke that you are the owner of this, right? So then in that case, Microsoft registers Microsoft.something, and they start giving out things which are very similar to email addresses. So Munib at Microsoft or Jude at Microsoft, right? And the interesting property there is that Microsoft still cannot revoke or take over my identity. It's just that my identity has an at Microsoft in it because it's registered as a subdomain to Microsoft. And this we can scale to billions of users.
Well, thank you.